This is lecture 5.3, Infinite Sets. In this video, we will state the basic properties of infinite sets and introduce the concepts of countability and uncountability of sets. To give a precise definition of an infinite set, we first recall the definition of a finite set. A set S is finite if and only if either it is empty or it is numerically equivalent to a set of integers from 1 to n for some positive integer n. A set is infinite if and only if it is not finite. That is, a set S is infinite if and only if the following conditions both hold. S is non-empty, and for any positive integer n, S is not numerically equivalent to the set of integers from 1 to n. Some conditions in order for a set to be infinite can be inferred from the properties of infinite sets. For instance, recall that if S is finite, then S is not numerically equivalent to any of its proper subsets. We can write this symbolically as follows. If S is finite, then for any proper subset T of S, S is not numerically equivalent to T. This is equivalent to its contrapositive, which is the statement if for some proper subset T of S, S is numerically equivalent to T, then S is infinite. This gives us the following sufficient condition for a set to be infinite. If S is numerically equivalent to one of its proper subsets, then S is infinite. We will use this condition to prove that the set of natural numbers is infinite. Consider the set 2n of even natural numbers. Then, 2n is a proper subset of n since 1 is a natural number but 1 is not even. We can show that the map f from n to 2n, which sends each natural number small n to 2 times small n, is a bijection. The details are left as an exercise. Therefore, n is numerically equivalent to 2n. So n is numerically equivalent to one of its proper subsets. Thus, by the result in the previous slide, n is infinite. This proves the theorem. The set of natural numbers represents one type of infinite set. A set S is said to be denumerable or countably infinite if and only if it is numerically equivalent to the set of natural numbers. The cardinality of such a set is represented by the symbol aleph naught. Observe that since a countably infinite set is infinite, its cardinality aleph naught is not a real number. To show that a set has cardinality aleph naught, we need to show that it is numerically equivalent to the set of natural numbers. For example, the set of positive integers and the set of non-negative integers both have cardinality aleph naught. Indeed, recall that depending on the convention being used, the set of natural numbers is either the set of positive integers or the set of non-negative integers. By exercise 1 in lecture 5.1, the set of positive integers is numerically equivalent to the set of non-negative integers. So, by the transitivity of numerical equivalence, the set of positive integers and the set of non-negative integers are both numerically equivalent to n. The set of all integers has cardinality aleph naught. Indeed, it is shown in exercise 6 in lecture 4.4 that the set of all integers is numerically equivalent to the set of positive integers. It follows from this in the previous example that the set of all integers is numerically equivalent to the set of natural numbers. For any positive integer m, the set of all multiples of m has cardinality aleph naught. Indeed, it is shown in exercise 7 in lecture 4.4 that the set of all multiples of m is numerically equivalent to the set of all integers. It follows from this and example 2 that the set of all multiples of m is numerically equivalent to the set of natural numbers. The Cartesian product of the set of natural numbers with itself has cardinality Aleph naught. Indeed, recall from exercise 8 in lecture 4.4 that the Cartesian product n times n is numerically equivalent to n. The set Q of natural numbers has cardinality Aleph naught. We defer the proof of this last example to lecture 5.4. We now obtain another sufficient condition in order for a set to be infinite. Recall that if S is finite, then every subset of S is also finite. We can write this in symbols as follows. If S is finite, then for any subset T of S, T is finite. This is equivalent to its contrapositive, which is the statement if for some subset T of S, T is infinite, then S is infinite. That is, if S has an infinite subset T, then S is infinite. We will use this condition to show that the set of real numbers is infinite. Consider the set N of natural numbers. N is a subset of R, and as we showed earlier, N is infinite. So R has a subset which is infinite. Therefore, by the previous result, R is infinite. We have another sufficient condition in order for a set to be infinite. Recall that if a set is finite, then every set which is numerically equivalent to S is finite. We can write this in symbols as follows. If S is finite, then for every set T, if T is numerically equivalent to S, then T is finite. This is equivalent to its contrapositive, which is the statement if for some set T, T is numerically equivalent to S and T is infinite, then S is infinite. That is, if S is numerically equivalent to some infinite set T, then S is infinite. We will use this result to prove that the open interval from 0 to 1 is infinite. Recall from exercise 9 in lecture 4.4 that the function g from the open interval from 0 to 1 to the set of real numbers, which sends each real number x to 2x minus 1 over x times x minus 1, is a bijection. So the open interval from 0 to 1 is numerically equivalent to the set of real numbers. We have shown that the set of real numbers is infinite. Therefore, the open interval from 0 to 1 is infinite. Thus, we have two sets, namely the set of natural numbers and the open interval from 0 to 1, which are both infinite. We will now show that these two sets are not numerically equivalent. For our proof, we will assume that the natural numbers are the positive integers. It is not difficult to adjust the proof if 0 is assumed to be a natural number. This is left as an exercise. In order to prove the theorem, we need to show that there is no bijection f from the set N to the open interval from 0 to 1. We will use the following fact about real numbers. For any real number x between 0 and 1, there exist unique digits a1, a2, and so on from 0 to 9, such that x can be written as a decimal 0.a1, a2, and so on. With the property that there is no index n, such that for all indices k starting from n, the digit a subscript k is equal to 9. A decimal satisfying this property is said to be in normalized form. For example, Using the formula for the sum of infinite geometric series, the number 1/2 can be written as 0.4 plus 9 times the summation of 1 over 10 raised to n from 2 to positive infinity. In decimal form, this is equal to 0.4999 and so on. All digits starting from the second position to the right of the decimal point are equal to 9. This decimal form of the number 1/2 is not normalized. We know that 1/2 is equal to the decimal 0.5. Since there is no infinite sequence of nines in 0.5, this decimal is in normalized form. We now prove the theorem. For the sake of a contradiction, assume that the open interval from 0 to 1 is numerically equivalent to n. Then there is a bijection f from n to the open interval from 0 to 1. For each natural number small n, write the image f of small n in normalized decimal form 0.a sub n1, a sub n2, a sub n3, and so on. Define the number b as follows. B has decimal form 0.b1, b2, b3, and so on, where for each natural number small n, the digit b subscript n in the nth decimal place is 1 if the digit a sub nn, that is, the digit in the nth decimal place in the image of f of n, is not equal to 1. And 2 if the digit a sub nn is equal to 1. Then the number b defined in this way lies between 0 and 1. And for any natural number n, the nth decimal digit b sub n of b is never equal to a sub nn. So b is not equal to the image f of n, and this holds for all natural numbers n. Therefore, b does not belong to the range of the function f, which implies that f is not a surjective function. This gives rise to a contradiction since f is a bijection from n to the open interval from 0 to 1. Hence, there is no bijection f from n to the open interval from 0 to 1. This proves that the open interval from 0 to 1 is not numerically equivalent to n. This fact motivates the following definition. Let S be a set which is numerically equivalent to the open interval from 0 to 1, or the set of real numbers. Then the cardinality of S is denoted by the symbol C, which is short for continuum. Since the open interval from 0 to 1 is not numerically equivalent to the set of natural numbers, it follows that C is not equal to Aleph naught. Here are some other sets that also have cardinality C. The set of positive real numbers. This follows from lecture 5.1 exercise 3, which claims that the set of positive real numbers is numerically equivalent to the set of all real numbers. The set C star of all points on the circle x squared plus y squared equals y, except for the point 0, 1. This follows from lecture 4.4 exercise 10, which claims that C star is numerically equivalent to R. Any open interval with endpoints A and B. This follows from lecture 5.1 exercise 2, which claims that an open interval from A to B is numerically equivalent to the open interval from 0 to 1. For the remaining examples, we omit the proof as this is beyond the scope of our course. Any interval with endpoints A and B for real numbers A and B. The set of irrational numbers, the power set of n, and the set of all ordered pairs of real numbers. All of these sets have cardinality C. We are now able to define a new classification of sets. A set is said to be countable if and only if it is either finite or countably infinite. Otherwise, the set is uncountable. In particular, the null set, the set of integers from 1 to n for any positive integer n, and the set of natural numbers are all countable sets. The set of real numbers and the open interval from 0 to 1 are both uncountable. You have come to the end of lecture 5.3. You may now proceed to lecture 5.4. Thank you for your attention.